Hey everyone, this video will cover the do file for regression and confounding. And apologies if you hear shrieking in the background. That would be my daughter and husband outside on this lovely 50-degree day shooting water cannons at each other. So we are going to go down to the regression section of the class website in just a second. I just want to remind you, since this may be the first time that you're attempting to use UDesk to access Stata, that there are links under the Stata resources page, including the direct link to UDesk itself. And then right below that is still our campus wellness assessment data area. So you'll need the data set for 2019 to 2020. And again, I've updated that. We were using the 17-18 questionnaire before, but we're gonna move to the newer one now. So if you go ahead and scroll on down to the regression modeling and confounding section of the website, you'll see this do file for regression and confounding. And so that's what I'm gonna be covering today. So go ahead and open Stata, and you can open the campus wellness data set. Oops, I don't have it in my downloads folder on my personal computer, so I'm gonna go back and get that real quick. Okay, sorry, back to the top. Okay. So I'm gonna save the wellness assessment to my downloads folder and then go back over to Stata, and now I should be able to open it. All right. And as usual, we can confirm that it opened because now we see variables listed over here at the top right-hand side of the page. And then I'm going to open a new do file editor. So remember, that's the little pencil and paper looking icon up here at the top. And go back to as you learn. And now go down to the regression section and open that do file there. So I'm going to do Control A and Control C to copy it. And I don't know why that became so big all of a sudden. And paste it over here in my do file window. All right, so in the earlier lectures I posted, I talked about the basics of both linear and logistic regression. And again, even though we will be using logistic regression alone for your class projects, I do want to still show you what linear regression looks like. And so we're going to be using one of the sample data sets that's posted on the UCLA website that we've used before. And before I jump into this, let me just give you the takeaway. So the commands to do regression in Stata are pretty straightforward. So for linear regression, the command is regress. And then for logistic regression, the command is logistic. And the format for both of them is the same. You actually kind of write the variables out in the same way that they look in the equation that we talked about before. So where we have the expectation of y equals beta naught plus beta 1 x1 plus beta 2 x2, etc. That's the same order that we're going to write our variable names in. So we're going to put the outcome first and then list all of the exposure and all of the confounding variables after that. So same format for logistic regression. You say logistic, the name of your outcome variable, the name of your exposure variable, and then anything else you're adjusting for. So let's do some specific examples. So row 19 of the code that I have showing here is to open this crime data set from that UCLA website. And we can use the describe command to look at what's in there. So it has an ID number, the state, the name of the state. Then there are a bunch of numeric measures after that. So there's a crime rate, violent crime rate, and a murder rate. Then there's the percent of the state that is considered metropolitan. So it's kind of like an urban measure. Percent of the state that has people who are classified as white. Percent of people in the state who have graduated from high school. or had a higher level of education, percent living in poverty, and then the percent of households that are single parent. So it's a pretty small data set in terms of the number of variables. And let's just look at what some of these values look like. So if we just do tab poverty to look at what the poverty percentages look like, you can see that it's basically a quantitative measure. So it's not categories, it's actual numbers to one decimal place of the percentage of people, residents in each state that live in poverty. And so it ranges from 8 to, if we click more, down to 26.4%. So a pretty wide range of poverty. And then the murder rates, similarly, are numbers, they're numeric, quantitative variable. So it ranges from 1.6 to 78.5, so an even wider range there. But you can see most of them kind of fall in this 1 to 13 range, and then there's one state that has 20 and one state that has 78. Okay, another way, we haven't really done this much since we have so many qualitative, or we have entirely qualitative variables in our data set, but the summarize command, which I've abbreviated here as SUMM, if we summarize poverty and murder, it's a little bit easier to see than a big table like the ones above because there's so many different values. So it tells us for both of these, there's 51 observations. I think it's the 50 states and DC. And it tells you what the mean is and the standard deviation for each measure. And it also gives us the minimum and maximum. So we can see those ranges that we saw above. Okay, so let's say that our question of interest is whether poverty impacts murder. So does the percent of households in poverty, is it associated with the murder rate in a state? So this command here on row 39 will help us answer that question. So again, regress means linear regression. So we're asking Stata to run a linear regression where the murder rate is the outcome. So we list that first. And the poverty rate is the explanatory variable or the exposure that we're interested in looking at. And so if we run that, we get these results here, which are already in your sample code, but I'll switch over to this window since it's a little easier to read. So there's some information about the model itself, the sum of squares, degrees of freedom, and these are informative, but we're not going to focus a lot on them in this class, so I'm going to kind of skip over that. The one thing I do want you to be aware of anytime you're running regression models is the number of observations. So in this case, we have 51 observations. Again, that's what we saw above, so that's good news. Basically, every state in this data set is represented in our regression model. And as we go along, you'll see that depending on what you include as covariates in your model, your number of observations will change. So Stata, as other programs, require that in order to be included in a regression model, that the person or the row of data have information on every one of the variables contained within it. So as we said before, our new data set has about 1,550 people in it. And so you want to make sure that your number of observations is about that high. Certainly if you start seeing something like 400 or 600 observations, you know you've somehow lost people along the way. But it's important to look at the variables as well so you know how many people to expect in this number of observations. And since we saw up here, that there are 51 observations in both of these variables, that is indeed what we would expect to see here. So that's good news. These other measures here also tell us some about the model itself and whether or not the explanatory variable seems to be doing a good job of giving us information about the outcome. So for example, this adjusted R-square, it's kind of like a correlation value. So it tells us how much of the data in the poverty variable and the murder variable are similar. So 0.3, not particularly high, that's about 30%. So not perfect, but a fair amount of the variability in the murder rate is explained by poverty. It's kind of what that's telling us. Okay, so let's talk about this part down here. The bottom of the table is mostly what you'll be focusing on when you're reporting your results. So the first thing we see here is a coefficient for poverty. And so essentially what this is saying is that for every 1 unit increase in poverty, which in this case is a 1% change in the poverty rate in the state, the murder rate goes up. We would expect the murder rate to go up by 1.3. And it doesn't label what the murder rate is. I'm assuming that's per 100,000 people in the population, so that's how I'll be talking about it. So again, this would mean that for a 1% change, a 1% increase in the poverty rate in a state, we would expect the murder rate to increase, because this is a positive number, by 1.3 per 100,000 people. We can go over here and see that that confidence interval ranges anywhere between about 0.8 per 100,000 and 1.9 per 100,000 people. This confidence interval does not include 0. So if you recall, the null hypothesis for this test is that the poverty rate does not change the murder rate. That's our null hypothesis for a regression, a linear regression model. And so if that were true, we would expect this coefficient to be 0. And so the fact that this confidence interval does not include 0 is a pretty good indicator that we're going to reject our null hypothesis. Our null hypothesis, our 0, is not within that confidence interval range. And so most likely it is not true that there is no difference in the murder rate based on the poverty rate in a state. But to confirm that, we want to look at our p-value. And so that's our p greater than the absolute value of t column here. And so it's just a bunch of zeros, which we would report as p less than 0.001. And since that is less than our critical alpha value of 0.05 that we just use by default, we would indeed reject the null hypothesis. So essentially this table is telling us that there is a statistically significant association between the poverty rate in the state and in the murder rate. So I have written most of this here, including this equation. So this is what this model, if you wrote the model that Stata is running out in statistical notation, it would be that the expectation of y, or the expectation of the murder rate, is equal to beta naught plus beta 1 times the poverty rate. And so beta naught is the coefficient for the constant value, so that's the intercept of the model, which I didn't talk about yet, but that's the second row in the output here. So this is saying, this model is saying that if there is no poverty in the state, so if the poverty rate were 0, you would plug in a 0 here, which would mean it would cancel out this beta 1, and we would only be left with the beta naught. Saying if there were no poverty in a state, then the murder rate would be negative 10.1 per 100,000. So that's clearly problematic. Obviously, a murder rate cannot be negative. So this model isn't perfect. We can tell that already, that it's not a perfect explanation of the murder rate. But given that 8 was the lowest poverty rate that we observed in the data set, if you go down here a little bit, I've calculated that for you. So when we use that lowest rate, the lowest observed poverty rate in our data set, which represents the entire US, we would calculate a murder rate of 0.4 per 100,000 people. So the good news is it works well enough for the values we've observed. The bad news is that it's not possible that this is truly the model that represents the relationship between poverty and the murder rate, because it gives us an impossible number for the case when there is no poverty. Let's see. So the other nice thing about these regression models is you can actually plug in values. So let's say, for example, you want to know what our murder rate in our state might look like if our poverty rate were 25%. You can just plug that 25 in as the X value. So multiply 25 by the poverty coefficient, this 1.32. Subtract off our intercept of negative 10. And then we'd estimate our murder rate would be about 23 per 100,000 people. Oh, my not equals signs, sorry, did not get transferred very well. But the alternative again is that beta 1 is not equal to 0, that there is not no difference between the murder rate depending on what the poverty rate is. Okay. So unfortunately, I can't ask you if you have questions, but hopefully that makes some sense. We're going to do one more. Actually, I probably won't go through this example here. There is another example looking at using this home sales data set, which we're going to go ahead and open because I'm also going to use it for the logistic regression example below. But in the interest of time and knowing that you're not actually going to be running linear regression models for your class project, I just want to note that there's another example here. So you could do it on your own, maybe delete the part of the code where I give you the output, just so you can make sure you understand both how to run it and then how to interpret the results. But let's use this home sales data set, and I'll describe that as well. Another relatively small data set in terms of the number of variables, just 5 of them. And we can see there's 93 observations in this data set. And this has to do with home prices and characteristics of homes. So the variable called price is the selling price of the house in thousands of dollars. The size represents the square footage in thousands of square feet. And then the last few variables are the number of bedrooms, the number of bathrooms, and then just a binary indicator of whether or not the home was new. So we're going to use this data set to skip down here and do logistic regression. And as we talked about in the other videos, logistic regression requires that your outcome is dichotomous. So it has to only have 2 categories, a yes category and a no category. I strongly recommend that you code the no as 0 and the yes as 1, because that will help in terms of what state it chooses as your outcome variable. Because if you remember when we were talking about what a logistic regression model is it's modeling the probability of success, the odds of the probability of success. And success is a value of 1, so of the outcome happening. Okay. So this first model here, in row 196 of my sample code here, is asking Stata to run a logistic regression model where we're predicting whether or not the house is new. So that's, again, just a yes/no variable. It's either new or old. And we want to see if the price that the home sold for can help us understand whether or not it was new. So let's run this logistic new price model. And so we get this output here. It has a little bit less information than the linear regression model above did. Still tells us the number of observations, so that's important to check. 93, that's every observation in this data set, so that's good news. And you can also kind of look at the pseudo R-squared. We can't calculate the R-squared in this case directly, but about 11% of the variability in whether or not the house is new is explained by the price of the house. So a pretty small percentage. So let's come down here to our output and talk about what these numbers in this price row mean, because that's our main interest. We want to know, does the price of the home tell us anything about whether or not the home is new construction? So the first number here is the odds ratio. And that's actually what the logistic command gives us. There's also a logic command that would run exactly the same model, but instead of giving you the exponentiated estimates, it gives you the estimates themselves. And so I like using logistic just because it exponentiates them for you. And this is really what we want to report. So our odds ratio is 1.02. And remember that in this case, for logistic models, the null hypothesis is, again, that there's no difference, in the likelihood, the odds that a house is new given what its price is. And another way to state that is that the odds ratio is equal to 1. So remember that, as we talked about in the kind of lecture session, an odds ratio of 1 means there's exactly the same odds of the outcome for the exposed group and for the unexposed group. Now, in this case, we have price as a quantitative variable, so there's not just an exposed and unexposed group. But basically, we could say for any 1 unit higher price, so for $1,000 higher priced home versus, you know, $1,000 lower priced home, what is the odds that the house would be new? And so our null hypothesis is that there is no difference, which means the ratio is 1. The odds ratio is 1. So that's our null. And our alternative is just that our odds ratio is different than 1. But there is some difference in the odds of a home being new based on what the price is. So let's again look at the confidence interval, and we see it goes from just above 1. So this would round to about 1.01 to 1.04. And again, our null hypothesis is that the odds ratio is equal to 1, and 1 itself is outside of this confidence interval. It's not contained within this confidence interval. So most likely that's evidence that we're going to reject the null. And we confirm that here. Now our column is that P is greater than the absolute value of Z rather than T. We're looking at T statistics above in the linear regression models. Here we're looking at Z-score based statistics for logistic models, but our p-value is 0.004, so clearly less than 0.05. So we do indeed reject the null hypothesis. So we would conclude that there is a statistically significant association between the price of a home and whether or not it is new construction. And in particular, one way we could say this is that for every $1,000 increase in price, because that would be a 1 unit change since price is reported in thousands of dollars in this data set, for every $1,000 increase in price, the odds that the home is new increase by 1.02 fold or by 2%. So it's a small change, but you can imagine then as you increase by $10,000 or $20,000, that odds ratio, gets larger. So a small but statistically significant increase in the odds that a home is new versus old for every $1,000 in price increase, or in higher price, because these are sale prices. Now we can also look at, maybe we want to say, okay, can we get any information about the odds of a home being new based on the number of bathrooms that are in the house? And so this model would be logistic new bathrooms. And we can see here, we still have 93 observations. That's good news. Pseudo R-squared is only 2%, 3%. So not even as much explanation of the variance as we saw above. But we get a pretty big odds ratio here. So this is saying that for every additional bathroom in a home, the odds of it being new increase by about 2.9. You have almost 3 times higher odds of the home being new if there's 1 additional bathroom. However, this is not statistically significant. So our p-value is greater than 0.05. 1 is contained within our confidence interval here. So we'd say there's no evidence that this is a statistical relationship. There's no statistically significant difference. So we would fail to reject our null hypothesis in this case, which again is that there is no difference in the odds of a home being new based on having an additional bathroom. But actually a better way to run this, a better way to include categorical models or categorical variables in models is to precede the variable name with an I and a period. And so we might decide to do that here because bathrooms, it is a count of the number of bathrooms, but there are only so many bathrooms a house can have. So maybe you want to say, I want to know, 1 versus 2 bathrooms or 2 versus 3, not just any 1 unit increase in bathrooms. And so let's say we change our model and do logistic new I dot bathrooms, because the I with a period tells Stata that the variable is not a quantitative variable, it is qualitative. It has different categories, and you want to treat it that way in the regression model. So the bad news in this case, you can see that the values for bathrooms are 1, 2, and 3, but we see this kind of strange looking output here. So we get a note from Stata right under our code that says, if bathrooms is not equal to 0, that predicts failure perfectly. So that means it's not a new house. Predicting failure means being an old house. And then it says that one of the categories was dropped. So if bathrooms was 3 because of collinearity. And so that probably means that every home with 3 bathrooms was new. So it's kind of the same problem that none of the new homes had 0 bathrooms and all of the houses with 3 bathrooms were new. So both of those are problems. If you think about it as a 2x2 table, which I think I have here. Yes, so if we cross tab bathrooms and new, you can see that we have a 0 here. So in homes, there were 10 homes with 1 bathroom, but all 10 of them were old. And so that's problematic. And anytime you have a 0 in one of your cells in a 2x2 table, you're going to run into problems in your regression model. So it's always good to check crosstab things before you run a regression model to make sure that your data set can actually support you running the model that you want to run. So this is just an illustration that while you might want to know about bathrooms as a categorical variable, that it may not be possible based on the distribution of data within the sample that you've collected. So always remember to check that. So the last part we're going to do here is that we are actually going to use our campus wellness data set to run a logistic regression model. So I'm going to open that data set again. Okay. So in this example, I'm going to be looking at a topic I've used as an example in class before. So whether or not sleep is different for students who are parents or guardians of children compared to students who don't have children or aren't guardians of children. So those 2 variable names in our data set, the sleep variable is represented by this sleep 7, and the parent variable is, well, the parent variable name represents the variable that asked about whether or not students are parents or guardians of young children. So I don't have this in there, but just as a reminder, we could tab sleep 7 and tab parent just to see what the response options are. So just by looking at this, you can see sleep 7 has 4 categories. So people reported the number of days in the last week when they got 7 to 9 hours of sleep. And the parent variable is just yes or no, so 2 categories. And as I said above, we want to at least make sure that we don't have any zeros in cells here. So let's cross tab those 2. So good news, no zeros. We can certainly run this crude model, so the model that just has parent and sleep in it. And so that's a good starting point for this. So let's say you ran this regression model and you typed logistic sleep 7. So we want to know if there's a relationship. We know that there is, these are cross-sectional data, and I've said in class it usually is kind of up to you which you want to be the exposure and which one you want to be the outcome. So let's say you want sleep to be the outcome, so you run logistic sleep 7 parent. And hopefully you could see this coming, that this won't work because it says in this note we get here from Stata, it says outcome doesn't vary. Remember 0 means a negative outcome and any other non-missing values are a positive outcome. So first of all, there's no 0 in the sleep 7 variable, but we also need it to be dichotomous. So we need a 0, 1 sleep variable in order to run this regression. And this would have been, we were hoping that this would tell us, does parent status influence your sleep? Which would be the right way to do it, because parent status, whether or not you have kids, is probably not going to be influenced by sleep. In other words, it makes a lot more sense for parent status to influence your sleep than for the amount of sleep that you get to influence whether or not you have a child. So this is the correct order conceptually. We want sleep to be the outcome and parent status to be the exposure. But let's say, you know, you're in a rush and you just think, well, I'll flip them around then because parent status is binary. So I could use that as my outcome and put sleep as the exposure. And it runs. We get an answer here. We have 1,520 people who were included in this regression model. But as I note in the code over here, it doesn't answer our question. We want to know if students who are parents get different amounts of sleep than students who aren't parents. And this is telling us that do students with different amounts of sleep have different odds of being a parent. So we can sort of interpret this nonetheless. It doesn't make a terrible amount of sense, sorry. But what this is saying, this odds ratio here of 0.87, means that for every 1 unit increase in sleep, and here a 1 unit increase in sleep is not a completely direct thing because we have these categories, but as it's basically saying, as you go from 0 to 1 days to 2 to 3, or from 2 to 3 to 4 to 5, or from 4 to 5 days to 6 to 7 days, as you make each one of those jumps in the amount of basically the number of nights on which you got enough sleep in the past week, you are less and less likely to be a parent. So as you get more and more sleep, the odds that you are a parent is essentially going down here because the odds ratio is less than 1, which means that an increase in the exposure, an increase in the number of nights you got adequate sleep is actually associated with less of the outcome, the lower odds of having the outcome, which in this case is being a parent. So as I mentioned in the lecture portion, these odds ratios that are less than 1 can be a little bit less intuitive to interpret. So don't worry too much if that is still confusing for now. We'll do some more examples and I can help you through it if you end up getting an odds ratio like this. But let's finish looking at this output here for now. Our confidence interval goes from 0.68 to 1.1. So remember our null here would be that the odds ratio is equal to 1, that there is no difference in the odds of being a parent based on how much sleep you get. And so 1 is contained within this confidence interval, and we can confirm here with our p-value. Our p-value is 0.26, so clearly greater than 0.05. So we fail to reject the null here. So there's no statistical evidence in this model that sleep influences your parent status. An even better way to do this, as I said from the last example, given that sleep, yes, there are 4 different categories, but they're not really, it's not a quantitative variable. It's a number of nights per week, and a 1 represents 0 to 1 days. Really a better way to write this model would be logistic parent I dot sleep 7. So Stata will treat sleep as a categorical variable instead of a continuous variable. And so now our output looks different. We still have 1,520 people included in the regression, but our sleep, instead of getting just 1 odds ratio for sleep 7, we get a different odds ratio for each category. And so this is saying, compared back to the group who's not showing, so there is a 0 to 1 days group. So there are reference category. And so this first odds ratio, for example, is saying that compared to students who said they got 7 to 9 hours of sleep on 0 to 1 days in the past week, the odds of them being a parent are 0.3 times as high. So if you did 1 minus 0.3, this is about a 67% lower odds of being a parent if you said you got 7 to 9 hours of sleep on 2 or 3 days in the past week. And this one is statistically significant. This next one is saying that for students who got 7 to 9 hours of sleep on 4 to 5 days in the past week, compared to those who got 7 to 9 hours on 0 to 1 days, so same reference group, those students with 4 or 5 days have 0.6 times the odds of being a parent. That category is not statistically significant. And then the last one here is for students who got enough sleep on 6 or 7 days versus 0 to 1 days, they have 0.5 times the odds of being a parent. Also not statistically significant. So overall, we would conclude that there seems to be a relationship between sleep and parent status, but only at the low end of the sleep spectrum. For students getting 4 days or more, there's no significant relationship between the two. But as I said before, this is not really answering a question that is terribly useful from a scientific, from a public health perspective. So let's go back and do a better model. Let's do the model that we really wanted to do in the beginning, which is to treat parent status as the exposure and sleep as the outcome. So in order to do that, we first need to turn sleep into a binary or dichotomous variable. And so that's what this section of code here is doing. So line 360 is just giving us the tab of sleep again, reminding us what those categories are. And this is a piece of code that we didn't talk about before. We've always kind of done a generate statement first to make a new variable and then replaced it with different values. This is just another option. That approach would work just fine. And if you're interested in seeing what that code would look like, I can send it to you or post it on the class website. But I'm using this recode command, which kind of does it all in one step. So what I'm saying is I'm asking Stata to recode this sleep 7 variable that already exists. And I'm going to make it so that if the person said that they got 7 to 9 hours of sleep on 0 to 1 days or 2 to 3 days, so that's this 1/2. In Stata, the slash means through, so you can't use a little dash like a hyphen, because that's also a minus sign, right? So 1/2 means if the value of sleep 7 was 1 through 2, so 1 or 2, then make our new variable equal to 0. And if the sleep 7 variable was 3 or 4, which represents 4 to 5 days or 6 to 7 days, then make our new variable equal to 1. And then you do a comma and a G or generate. This is where the generate statement comes in. And you put in parentheses the name that you want to call the new variable. So I'm saying make a new variable using this definition and call it adequate_sleep. Then I can still label that variable like we've done before. This just will be so that instead of showing the name adequate sleep, like here in the table, it'll show sleep 7 to 9 hours on 4 to 7 days. I'm also going to label my values so that 0 shows up as no and 1 shows up as yes. And then I can cross tab. Let me go ahead and run this. Those two to make sure I made them correctly, and I probably should add comma M so it shows me the missing values too. So it looks like this is correct. All my people who said they got 0 to 1 or 2 to 3 days on which they slept 7 to 9 hours in the past week, they're coded as no's. My 4 to 7 days are coded as yes. And then the 33 people who didn't answer the sleep question are still missing in my new variable. Okay. So we can see 1,524 people is how many we will expect to see in a regression model potentially. And then if I wanted to go back and do the chi-square test, which you all have done before for previous assignments, I would just do tab adequate sleep parent, comma, COL for column percentage and CHI with chi-square test. And you can see that based on this chi-square test, there's no relationship between my definition of enough sleep, of adequate sleep, and parent status. And as we've talked about before, I have this interpretation down here. So this is saying that among students who are not parents, 45.5% of them got enough sleep. And among students who are parents, 47% of them got enough sleep. So you can see those two numbers are pretty similar to each other. And our p-value down here is 0.76. So we would fail to reject the null and say there's no evidence of a statistically significant relationship between these two variables. Nonetheless, let's go ahead and run our regression model. So now, because I've made this adequate sleep variable that is dichotomous, I can run logistic adequate sleep I.parent So this I dot here is not critical because parent only has two categories, but it's just good to be in the practice of preceding any qualitative variable with an I and a period. The exception is, you might notice I don't have anything before adequate sleep over here, but because this is a logistic regression model, you must have a qualitative variable as your outcome. So state is basically assuming that this is a qualitative variable, and then everything on the what would be the right side of the equation, you need to indicate to Stata whether it's qualitative or quantitative. Okay, so if we run this, we get an odds ratio of 1.07. So that's telling us that students who are parents have 1.07 times the odds of getting adequate sleep compared to students who are not parents. So this odds ratio is higher than 1, which means that parents are actually a little bit more likely to get adequate sleep based on this definition. They're 7% more likely to get adequate sleep, or have 7% higher odds of getting adequate sleep. But if we look at our confidence interval, it includes 1, and our p-value is 0.763, which is the same that it was in our chi-square test above. So no significant difference between parent status and sleep among our students here. But let's say that I want to adjust this model for confounding, because I think that there may be differences between students who are parents and students who aren't, and that might influence the relationship with sleep. And so in this next example on row 418 of this code, I am adding some confounding variables into my model. So it starts off the same, logistic adequate sleep, I dot parent, and then I can just keep listing all of the other confounding variables after that. So in this example, I'm going to adjust for age. Remember, like everything else in this data set, is a qualitative variable. So we have those two age categories, 17 to 20 and 21 or older. Male is just yes or no. So it's male versus female or intersex respondents. And then we have that question about anxiety in our campus wellness assessment. And that is also just yes, no, have you experienced anxiety in the past year? So when we run this model, this is still our primary interest here, this parent row. So remember that above we were estimating an odds ratio of 1.07. It was not statistically significant. And now we find that among students who have the same age, sex, and anxiety status, students who are parents are still not more likely than students who are not parents to get enough sleep. So this odds ratio has actually, we'd call this, it has been attenuated, which means it's even closer to the null, which is 1.0. It went from 1.07 to 1.01. So it's gotten even closer to 1 when we adjusted for other variables. Still not significantly different. Our p-value is 0.95, so we still fail to reject the null. So this is telling us that even if we account for differences between these students that might be confusing the relationship between parent status and sleep, there's still no relationship. We still find no evidence of a statistically significant association between students who are parents and getting adequate sleep. Now, it's sometimes also interesting to see which, if any, of your confounding variables do impact your outcome. And so I'll give you a second to look at these 3 p-values and think about which one is significantly associated with sleep. So if you said anxiety, you would be correct. So anxiety is the only one that has a p-value less than 0.05. And so that means we would reject the null for that row, the null being that sleep is similar for students with and without anxiety. So we would reject that null hypothesis for this test and say there is evidence that anxiety is statistically related to sleep. And if we were to interpret this, again, we get a p-value, we get an odds ratio less than 1 here. So this means that students with anxiety are about half have about half the odds, or 0.47 times as likely to get adequate sleep as students who don't have anxiety. So again, this interpretation has nothing to do with parent status other than it is actually accounting for whether or not students have the same parent status, age status, and sex. But the interpretation here is just about the relationship between anxiety and sleep. Sleep is the outcome. So again, this is saying students with anxiety are 0.47 times as likely to get adequate sleep as students without anxiety. P-value is less than 0.001. So we do reject the null again there and conclude that there's statistically significant relationship between the two. One other thing to note, so when we go back up to this model, there were 1,520 students included in the parent and sleep model. Down here, there are 1,513, so we've lost 7 students. And so they must be missing one of these 3 variables. And again, this is where we've already talked about how to put together table 1 and see what things are missing, what the frequency of missing is in your data set. So it is good practice to cross-check that. I'm not going to do it here, but you'd want to make sure that you were expecting to see 1,513, considering all the variables that you've got included in your model. Let's see if there's anything else I wanted to say. The rest of this code, I do use that logit command just so you can see what it looks like if you get the unexponentiated estimates and how and why you might use them. I'm not going to talk about effect modification now. I think very few of you are going to be interested in that topic, but if you are, feel free to read on through the rest of this sample do file, but really the logistics section is the one that you're going to need, that you're going to be doing for your group project. So send me any questions that you have. Feel free to post questions on the general discussion board on the website, and I will be in touch with you soon.